So hi everyone, I'm Lalith, and today I'm going to be talking about the importance of replica selection when it comes to reducing tail latency in the context of cloud data stores. So a recurring pattern in the way people architect modern web services today is to have very large request fanouts, where even a single end-user request arriving at an app server can trigger tens to thousands of data accesses behind the scenes. When you have such kind of access patterns, the tail latency of these storage servers becomes rather important, because the more servers you query per end-user request, the more likely it is that the overall query time is going to be bottlenecked by the tail latency of your storage servers. And for this reason, it becomes very important to rein in the tail latencies at your storage tier. Now, if you take a closer look at these storage servers themselves, what we find is that performance fluctuations are the norm and not the exception. And this can lead to many sources of tail latency pathologies. And some of these sources include contention for shared resources, skewed access patterns, queuing delays across various layers of the stack, as well as background activities such as garbage collection and log compaction. Now, considering these characteristics, we ask the following question. How effective is replica selection when it comes to reducing tail latency in the context of replicated and partitioned data stores? That is, if clients need to select one out of multiple servers to service a request, to what extent can this degree of freedom allow clients to cope with server-side performance fluctuations? And this question is going to be the focus of my talk for today. Now, replica selection is challenging for many reasons. For instance, different servers can present different service times for the same request, and this profile of a server can be time-varying. And clients need a way to reliably observe, measure, and adapt to these performance fluctuations. But in designing such a reactive mechanism, clients need to ensure that they do not enter herd behaviors, where a large number of clients could end up spamming a single server in the hope that that server is going to give all of them the best response time, and in the process end up degrading that server's performance and again harming the latency tail. So we need to be very careful when designing replica selection mechanisms. But how bad of a problem is this really in practice? And to get a feel of that, we decided to focus on the Cassandra distributed database, which is a wide column data store designed for low latency reads and writes. And most importantly, Cassandra comes with an implementation of a replica selection scheme called dynamic snitching, wherein servers in a Cassandra cluster will route requests to replicas, which exhibit a better history of read latencies as well as lower I/O loads, with the hope of, again, reducing response times. So we decided to put Cassandra to the test. We turned to some experiments on Amazon EC2. We used a 15-node Cassandra cluster using M1X large instances. So these are instances backed by spinning disks. And we used the Yahoo Cloud Serving benchmark in order to generate read-heavy workloads. And the data set that we used was 500 million 1 kilobyte sized records, which amounted to roughly 100 gigs per node. And we used a Zipf and key access pattern in order to generate a skewed workload. And at the end of each of these experimental runs, we were looking at the load profile of individual Cassandra nodes in the cluster. And this load profile can be visualized per node using a graph such as this, where on the x-axis you have time, and on the y-axis you have the number of requests handled by the node in a 100 millisecond window. And because we're dealing with a skewed access pattern, we decided to focus on the most heavily utilized node in the cluster. And the kind of load profiles we were seeing were ones like this, where there's a lot of variability at very small time scales. And we're noticing that the most heavily utilized node is servicing as few as 0 requests in a 100 millisecond window, and this value shoots up to be as high as 400 and 500 requests in subsequent intervals. Not only that, we see a lot of vertical bursts in the load profile, which suggested evidence of synchronized herd behaviors as well, all of which we were able to confirm upon closer observation and instrumentation of the dynamic snitching mechanism, details of which are in the paper. But very importantly, we also observe that the 99.9 percentile tail latency is as high as 10 times the median latency as well, which suggested that there is a tail latency problem as well. So we took these findings and we cross-checked them with some engineers we knew at Spotify, who had also publicly reported some of their experiences with load imbalances on Cassandra, wherein some nodes going into garbage collection process would lead to various kinds of load spikes and tail latency problems as well. So convinced that this can be a problem in practice, we decided to set out and solve it. And in the rest of the talk, I'm going to discuss how we took a system exhibiting a load profile such as the one I've shown you here and turned it into something a lot more stable and load conditioned, while also leading to significant improvements at the tail latency as well as higher system throughput. And the system that allows us to do this is called C3. C3 is an adaptive replica selection mechanism that is robust to performance heterogeneity in the environment. And C3 achieves its objectives through a combination of two mechanisms, which we call replica ranking and distributed rate control. With replica ranking, C3 clients can prefer faster servers in order to improve their response times. And with distributed rate control, we ensure that a fleet of C3 clients do not collectively overwhelm individual servers in a Cassandra cluster, or in a cluster. So first, let's talk about replica ranking. Consider the following simple queuing system, where on the left we have a set of clients receiving bursts of requests, and on the right we have two servers, one with a service time of 2 milliseconds, and another with a service time of 6 milliseconds. The ideal allocation here to minimize latencies would be something like this, where we perfectly balance queue lengths across servers in proportion to their service time differences. And essentially what we're trying to do here is to balance the product of the queue size and service time across servers. And the challenge here is to achieve such an allocation, or to approximate such an allocation in a fully decentralized manner without clients having to go through a common coordination point. And as a first step in designing such a mechanism, we would need some kind of measurement of the queue size and service time across servers, and that's what we're going to do first. So every client, when it makes a request to a server, gets back two metrics in the response. The first is the queue size observed at the server at the time the response is being dispatched. And the second is the time it took for the server to service that request, and that is the service time. Now, if clients were to use this measurement as it is naively to perform replica ranking and to select servers, they're going to end up in herd behaviors and load oscillations all over again, which is what we're trying to avoid. And that is because what's missing in this picture is the fact that there are multiple clients in the system, and we need a way to account for that. And so we address that with what we call concurrency compensation, wherein instead of only using the queue size feedback that we get from the servers, clients also augment that information with the number of outstanding requests that they have to a server, scaled according to a weight parameter W. And the effect of this is that a client that has committed more requests to a server will be more likely to switch replicas because it sees longer queue lengths at the first server. And this allows clients to desynchronize. Now, we have a queue size estimate. Can we go ahead and compute the queue size and service time product in order to start selecting servers? Let's see how that would pan out if we were to use this as a scoring function to rank and select replicas. Consider the following system with two servers, one with service times of 4 milliseconds and the other with a service time of 20 milliseconds. Let's say we had a queue buildup of 20 requests at the slower server. If we use the scoring function, clients would aim to have 100 requests queued up at the faster server before it switches servers again. And this is bad primarily because we already established that performance fluctuations are the norm and not the exception. What if the server hits a garbage collection pause? And if that would happen, you would lose 100 requests to the long tail, and we don't want that. And so this kind of queue size explosion at the faster servers is something we'd really like to avoid, and we really want to penalize long queues. And to do that, we borrow a leaf from some literature in flexible server scheduling, and specifically the idea of convex delay costs. And the idea is to switch some more weight to the queue size term in the ranking function. So instead of making the ranking function linear with respect to the queue size, we go for a higher power, such as a quadratic or a cubic term. And what this allows us to express in the scoring function is the idea that with every subsequent request that a client commits to a server, it inflates the risk associated with selecting that server again. And to visualize what would happen if we were to use a cubic function, let's go back to the same example that we showed in the previous slide, where we have 20 requests queued up at the slower server. With the cubic function, what would happen is clients would aim to have 35 requests queued up at the faster server before they switch replicas again. And this makes the system quite robust to performance fluctuations. And in particular, it gives us some protection at the latency tail. This is only the gist of the replica ranking mechanism that we use. And for more details, I encourage you to have a look at the paper. So that was replica ranking. Now let's talk about distributed rate control. First of all, why do we need rate control at all? And the point is that replica ranking on its own is insufficient, because with replica ranking, we cannot ensure that a fleet of C3 clients will not collectively exceed the capacities of individual servers that are in the system. And not only that, with replica ranking, we are observing the queue size and the service time from a single vantage point inside the server. What about sources of performance fluctuations that we cannot necessarily observe from that vantage point? And end-to-end rate control from a client to a server is a very good way of achieving this kind of reactivity. And so we use cubic rate control inspired by TCP cubic. And the idea is that clients estimate a saturation rate for each server, marked by the red bar here, or termed R0, and they adjust their sending rates over time according to a cubic function with the saturation rate as the origin. If at any point the client observes that the rate at which it is sending requests to a server is not catching up with the rate at which the client is receiving responses from the server, clients treat that as a congestion signal in order to multiplicatively decrease and then resume with the rate control again. So how do we put these pieces together? So there are a bunch of C3 clients in the system. Clients get requests which are directed to a replica group scheduler. And a replica group is a set of replicas in the system which can service a particular kind of request. So if I were to take the Cassandra example and we have replication factors of 3, you would have multiple sets of 3 replicas, each of which is a replica group. So you have a scheduler per replica group, and what the scheduler does is that it will sort the replicas according to the ranking function. It will select the first server that is still within the rate limit as established by the cubic rate adaptation mechanism. Every time a server responds to a client, it also piggybacks the feedback, which is used again to update the scoring functions. And if at any point we observe that the rate limiters, all rate limiters for a replica group have exceeded their rate limits, the system exerts back pressure and clients hold on to the request until a rate limiter is free again. We have implemented C3 inside Cassandra. I will not discuss the implementation details in the interest of time. I encourage you to have a look at the paper and let us know what you think. So we now need to see if C3 works at all. So we turn to Amazon EC2 uncontrolled testbeds for experimentation with the real system. And we also used extensive discrete event simulations to study the C3 mechanism independently of running it within a system such as Cassandra. In the interest of time, I will only be discussing some of the results that we got from Amazon EC2. So the setup is identical to the one I discussed earlier. We have a 15-node Cassandra cluster. We used M1X large instances, so these are backed by spinning disks. The workloads are generated using the Yahoo Cloud Serving benchmark. And we generate read-heavy, update-heavy, and read-only workloads. The data set is 500 million 1 kilobyte sized records, so this translates to roughly 100 gigs per node. And we compare against Cassandra's dynamic snitching mechanism, which will be indicated in the subsequent slides as DS. So first, let's look at the 99.9 percentile latency when we use C3 and when we use dynamic snitching. The 3 sets of bar plots correspond to the results obtained when using the read-heavy, the read-only, and the update-heavy workloads. The red bar indicates the measurements when using C3, and the blue bars indicate the same when using dynamic snitching. Lower is better on all these graphs. What we find is that C3 improves the 99.9 percentile tail latency by factors of between 2 and 3 times. Not only that, C3 also improves the median and the mean latencies, so we're not really trading off the median for the tail here. And most importantly, C3 also improves the read throughput by between 26 and 43% in these experiments. And this is one of the most important takeaways of the system, that C3 does not trade off throughput, does not expose a fundamental trade-off between throughput and latency. And in fact, by making better use of the combined capacities of all the servers available in a replica group, C3 not only improves throughput, but also latency at the same time. Now, let's look at how C3 reacts to dynamic workload changes. Now, we start an experiment with 80 read-heavy workload generators. After 640 seconds, 40 update-heavy workload generators join the system. So we see a sudden surge of write traffic in the system. And this leads to various kinds of background processes on Cassandra, so it generates some interesting performance fluctuations. And we're going to observe the latency profile with and without C3. So we see two time series here. On the left, we have a time series of the read latencies observed with C3, and on the right, we have the same when using dynamic snitching. Both time series are smoothened with a rolling median to better reveal the underlying trend. The red bar here indicates the moment at which the write-heavy workload generators enter the system, and we see a sudden surge of write traffic. Notice that in both cases, between the two time series, C3's latency profile is a lot more stable than with dynamic snitching. And most importantly, the latency profile with C3 in the presence of the update-heavy traffic is better than when dynamic snitching is operating without the write-heavy traffic, suggesting that C3 does react very effectively to dynamic workload patterns. There are many more experiments that we've conducted, the results of which are in the paper. I do not have time to go through all of them, so I'll summarize some of the remaining experiments from the EC2 runs. So we conducted experiments using higher system load, so we had more workload generators. We also ran experiments with skewed record sizes, where the record sizes are Zipfian skewed, favoring smaller records. We also conducted experiments on instances backed by SSDs instead of spinning disks. And across all of these, we could still see greater than 3x improvement at the 99.9 percentile latency when using C3. Not only that, with the SSD experiments, for instance, we were seeing throughput improvements of up to 50% than with dynamic snitching. And all of this can be done when you control for herd behaviors and load oscillations while also carefully reacting to performance fluctuations. Now, what are we up to right now? We are currently running experiments under realistic conditions at SoundCloud and Spotify. We are also turning to numerical evaluations to better understand the stability characteristics of the C3 system. I mentioned that we used a rate adaptation mechanism that was adapted from TCP cubic, so we are also investigating alternative strategies. And lastly, we are also porting C3 to some of the popular Cassandra clients, such as Astinax and the DataStax Java driver. So to summarize, I began this talk by discussing the tail latency problem and asking the question of how we can cope with it effectively using replica selection. I demonstrated the challenge in designing robust replica selection schemes using the case study of Cassandra. I then discussed the design of C3, which uses a careful combination of replica ranking as well as distributed rate control in order to not only improve the latency tail, but also the mean and the median, while also leading to significantly improved load conditioning as well as higher system throughput. And with that, I thank you for your time. I'm now open for questions.
Robert Escriva from Cornell University.
Hi.
So in your experiments, it looks like you're probably running with only one as the consistency level for Cassandra, because if you were running with all, you can't actually select replicas.
Exactly.
So you're effectively backloading the latency savings that you're making onto the time to which a read becomes
Can you speak
visible.
a little louder? I can't hear you clearly.
Yeah. So you're pushing the latency to the read, so it's going to take longer for a read to necessarily see a write. If your algorithm pushes the write to one replica and a read to another, it's going to take time for those reads to actually become visible. Did you actually measure this latency?
You mean the time that you would incur for the consistency to catch up, you mean?
Yeah, there's a time between which Cassandra says you wrote the item, and which you can actually get the item back out of Cassandra.
Yeah.
And if you do the replica selection differently than what Cassandra has, you're going to increase that time. So the write completes sooner, but your result, which is that you want to be able to read the data you wrote, is still the same.
So we don't interfere with that part of the system in a way. So we've conducted experiments with the consistency level of 1. So like I mentioned earlier in the talk, we are focusing on reading one out of multiple replicas, which is the most common use case with Cassandra. Now that said, we are also conducting experiments right now with quorum reads. So at the end of the day, if you're going to, like the more replicas you need to read from, the less degree of freedom that you have to react to performance fluctuations. So that is a trade-off in the system.
But
now, we don't affect the consistency part in any way. Dynamic stitching doesn't take care of that either. So.
Well, but what I'm saying is the default Cassandra implementation will generally read from the replica that the others are writing to, so you will see the reads faster. So did your
I don't think Cassandra explicitly tries to do that.
Okay.
It does not have any information of which replicas have already received a particular write. It does not try to.
Let's take that information offline.
Okay, yeah.
Hello, Luis from GST. My question is more about what you just mentioned, the query reads or trying to submit concurrent reads to multiple replicas.
Yeah.
What's your opinion about that, and how would that compare to C3?
You mean request duplication?
Submit reads to multiple replicas and just take whoever replies first.
Yeah. So request duplication is something that you can layer on top of a replica selection scheme. And the thing is, you sacrifice throughput there. And at higher utilization, this can be a trade-off that maybe you don't want to incur. Now, like I said, we are also conducting experiments right now where you do read from multiple replicas. And even there, we already see improvements of using C3 over dynamic stitching. So even there, the fact that we are more careful about selecting replicas is already giving us pretty good results.
Thank you.
Yeah.
Chen-Hong Lee from Google. So I'm wondering whether you have data breaking down the contribution of these two techniques to the latency improvement.
Yeah, we've addressed this in the paper. So one thing is that replica ranking, wherein we try to measure the relative performance differences between servers, is what gives us really the best deal for the latency. And the distributed rate control just ensures that we are not hitting the saturation point of different servers. So we've conducted experiments in the paper where, first of all, we try to inject some latency into the network stack. And we find that the rate control is what actually picks it up and backs off. And then we've also conducted simulations where we do not try to do anything intelligent with replica ranking, and we only have rate control. And in that case, of course, your latency is not as good as it should be. So we really do need the combination of the two techniques to achieve the performance benefits that we do.
Okay, very quickly, last question.
Sure.
Hi, Paul Rexsteiner from PagerDuty. You were mentioning that you're going to be looking into token-aware replica selection, or at least coordinator node selection. Presumably, if you're using consistency level of 1 or a replication factor of 1, would that mean that you would just always be going towards the replica that actually holds the data? Or would you be needing to do that experiment in situations where there's actually a multiple replication factor and then choosing like amongst those only?
Yeah, so with token-aware clients, if you have a replication factor of 3, you would go to one out of the 3 that are available. So it's not that you always go to the same replica. And now the token-aware clients have dynamic snitching type of intelligence embedded in the client side. But they're not as mature as dynamic snitching itself. And there's a lot of churn in that area, which is why we didn't go that direction yet. But right now, people seem to be moving towards the data stacks driver. And we already have like a experimental implementation there, which we're trying out now.